Hello everyone, good afternoon. This is another video dealing with problems connected to capacitors. Let's jump into the first one. A 7.7 microfarad capacitor is charged by a 125 volt battery and then is disconnected from the battery. When this capacitor is then connected to a second initially uncharged capacitor, the final voltage on each capacitor is 15 volt. What is the value of the second capacitor? Okay, let's read this again and understand. So there are two capacitors in play here. One is a 7.7 microfarad capacitor, which is initially charged to 125 volt. And so it has a certain amount of charge on it, because it's pre-charged. And then this capacitor is connected to a second capacitor which has absolutely no charge on it. And the connection, of course, has to be in parallel. Because you can just connect one plate to the other one, say the left to the left and the right to the right. So that's how you're going to connect. And when you do that, the uncharged capacitor is going to get charged. That means the initial one is going to lose its charge. So they're going to share charges. So does this mean that the charges on both of them will be equal? No. Charges will flow from the charged capacitor to the uncharged capacitor until their voltages become equal. So that's the key point. They are going to attain a common voltage. They're going to have a common potential difference. And we're given the final voltage to be 15 volt. We have to find the value of the second capacitor. So we have to find the capacitance of the second capacitor. So this is the charge on the first capacitor, given by Qi is C1V1, and the final charge is Q sub F is C1 plus C2 Vf. Now why is it C1 plus C2? Because they are connected in parallel. So the total capacitance is the sum of the capacitances. And also remember that the charge is conserved. That means Qi is equal to Qf, because there's no additional charge coming in, which means we can put these two together, equal to each other, and we can separate the unknown value, which is C2. So there is some math in that, as you can see. I've divided by Vf on both sides, and then taken C1 to the left side, which makes it negative C1. And so you can once again take out C1 as a common factor. And C1 is 7.7 micro. The initial is 125 volt, the final is 15 minus 1, which will give us the answer as 5.6 times 10 to the negative 5 farad, which is 56 microfarad, because it is 56 times 10 to the negative 6 farad. So that's how we work out this problem. And I worked it out in another way, just showing you that we could have done it in one step. As you can see, we could just say voltage is the ratio of charge to capacitance. Voltage is the ratio of charge to capacitance. That's what you see there. And then voltage is 15. And then Q1 plus Q2 is, of course, 7.7 microcoulombs. That is, times 125, because Q1 is C1 times V1. And Q2 is 0. So that's why you don't see it here. Again, this is Q1, this whole thing is Q1 because it is C1 times V1. So we could have done it that way. It's the same thing. So here is the second question. if it takes 15 joules of energy to move a 0.25 millicoulomb charge from one plate of a 15 microfarad capacitor to the other, how much charge is on one plate? So this is talking about a single capacitor, and it says that it takes 15 joules of energy to move a charge of 0.25 millicoulomb from one plate to the other plate. So you're going this way, it takes that amount of work. So the work is given, or the energy is given, the charge that is moved is given, and the capacitance is given. So the question is, how much charge is on one plate? So we're looking for charge. Okay, let's do this. Work is the product of charge and voltage, because voltage is the ratio of work to charge. So work done is the product of charge and voltage. So the charge moved is given, the voltage is given. So I've rearranged that. 15 joules is the work. The charge moved is what? 0.25 millicoulomb, which should be 0.25 times 10 to the negative 3. Okay, so that's 0.25 times 10 to the negative 3. And then capacitance is the ratio of charge to voltage, which gives the charge as 15 times 10 to the minus 6, that's micro, into 75 times 10 to the 3, 75,000 volt, which gives 1.125 coulomb. Now notice that I have used the charge as 0.2 millicoulomb instead of 0.25. Take note of that. So it should have been 0.25, but I have used 0.2 here in place of the 0.25. Just be careful about that. Okay. Shall we move to the next one? Now, this is worked out assuming that there is not much change in the charge on one plate, because what we have moved is such a tiny amount of charge compared to what is already on there, okay? So we are assuming that moving this charge does not change the charge on the capacitor appreciably. It's like adding a drop of water into the ocean. So that's a minute change. Here's the third one. An electric field of 4.80 times 10 to the 5 volt per meter, that's E, caps E, is desired between two parallel plates. So we need to have that field. Each has an area of 21 centimeter squared. Okay, 21.0 centimeter squared. You know, centimeter squared has to be changed into meter. And the plates are separated by 0.250 centimeter of air. What charge must be on each plate? So here we're given the field. We have the area and the distance between the plates. We have to find Q. So we have to have a relation that connects the electric field to the charge. And we know that E, the electric field between the plates, is sigma by epsilon naught, where sigma is the surface density of charge. Let's get there. So E, which is the electric field, is given as 4.8 times 10 to the 5 volt per meter. Area, 21.0 centimeter squared, has to be changed. That's times 10 to the negative 4, because you have to divide by 100 times 100. 1 meter is 100 centimeter, but because it's centimeter square, we have to divide twice by 100. Again, D is 0.25 times 10 to the negative 2 meter. We're looking for Q. Electric field is sigma by epsilon naught, but sigma is Q by A. Surface density of charge, sigma, is Q by A. So right there, you have the substitution for sigma right there. It's Q by A. And then you rearrange that, and we get Q is equal to E times A times epsilon naught. We know all of these values, so just plug it in there and calculate. Epsilon naught, you know, is 8.85 times 10 to the negative 12. So, electric field multiplied by the area in meter squared multiplied by epsilon naught gives us the charge on each plate. And we get 8.92 times 10 to the negative 9 coulomb, which is actually 8.92 nanocoulomb. That's how we do this one. Let's look at number 4. An electric circuit was accidentally constructed using a 5.0 microfarad capacitor instead of the required 16 microfarad value. So the engineer made a mistake. So instead of getting 16 microfarads, he or she accidentally used 5.0. Without removing the 5.0 microfarad capacitor, what can a technician do or add to correct the circuit? Now that's a very simple question. We have 5, we need 16, so we just need to add 11 microfarads in. Is it in series or in parallel? That is the question. How do we need to add it? We need to add it in parallel. Because when you add it in parallel, the equivalent capacitance becomes the sum of the two. So 5 plus 11 would give 16. So all we got to do is, or all what the technician had to do is to add 11 microfarad in parallel. That is the question. Now, seemingly you can make it a big mathematical problem, but it's so simple. Bringing us to the next one. Okay, I'm just showing that. This is how it's connected. This is what you mean by a parallel connection. So that's C1, that is C2, and obviously there should be a source to which you connect it. So that is the kind of parallel arrangement that we're looking for. Number 5, consider 3 capacitors of capacitances, 3600 picofarad, 5800 picofarad, and 0.0100 microfarad. Okay, 2 of the capacitors are given in picofarad and 1 is in micro. Well, that's not good. You got to, be able to change the micro into pico or change the picos into micro. We need consistent units. The question is, what maximum and minimum capacitance can you form from these? How do you make the connection in each case? Again, easy. To get the maximum, you just put all 3 in parallel. To get the minimum, put all 3 in series. Let me show you. Okay. So we have 3600 times 10 to the negative 12. That's pico, which is actually 3.6 times 10 to the negative 9 farad. So that's 3.6 nanofarad. So I have decided to change everything into nanofarads. All right. Similarly, 5800 times 10 to the negative 12 is 5.8 times 10 to the negative 9 farad. Again, 5.8 nanofarad. And this is 10 to the negative 6 because it's in micro. But we can put that as 10.0 times 10 to the negative 9 farad. So everything is in 10 to the negative 9. All of them are in nanofarads. So to get the maximum, just put them in parallel, which will give you the sum of the 3. And in that case, you will get, again, C1 plus C2 plus C3. Let me speed this up. That is going to give 3.6 plus 5.8 plus 10. That is what we're going to get. Do not forget the 10 to the negative 9. So we get 19.4 nanofarad. To get the minimum, put them all in series, in which case the formula is 1 over C. Is 1 over C1 plus 1 over C2 plus 1 over C3. Do not forget that on the left-hand side, it's 1 over C. So after you do the right-hand side, that's not the answer. You got to take the reciprocal of that to get the answer. And many students forget to do that. So please remember that 1 over C is what you get. And then when you take the reciprocal, you get 1.82 nanofarad. That's the answer. Let's move on to the next one. So in the problem given below, C1 is equal to C3 is 8 microfarad. So the capacitors on top are both 8 microfarad. C2 is equal to C4 is 16 microfarad. So that is C2 right there, and that is C4. So each one is what? 16 microfarad. And then Q3, which is the charge on C3, is 23 microcoulomb. Find the charge on each of the other capacitors, and then the voltage across each capacitor, and the voltage VBA. So you've got to find the voltage across these 2 points. This is A, and then you have B here, so you got to find that. So there are 3 parts to this question. And it comes with a diagram, and you have to remember the most important idea is that when capacitors are connected in parallel, the voltages across them are the same. But if they're connected in series, the charge across them are the same. So that's important. Let me say that again. Whenever capacitors are connected in parallel, no matter what the values of the capacitances are, the voltage across them will be the same. But if they're connected in series, then the charge across them will be the same. So when you look at C1 and C2, they are in parallel. The voltage across both should be equal. Also, C3 is in parallel to C4. Again, the voltage across them must be the same. So that's the idea we're going to use. We're given the charge Q3. We know the charge Q3. We also know the capacitance C3, don't we? If you know the charge and the capacitance, you can calculate the voltage, can't you? Yes. And once you get the voltage on C3, you know the voltage on C4 must be the same. And now that you get the voltage on C4 and you know the value of C4, you can find the charge on C4. That's how we're going to progress. Okay. So voltage of C3 is equal to the voltage of C4 because they are in parallel. And voltage is what? Q3. It's the ratio of charge to capacitance. So since the voltages are equal, put those two equal to each other. And then I rearrange and calculate Q4 to be 46 microcoulomb. I hope you got that. So this is key. This is nothing but voltage, see? Ratio of charge to capacitance is voltage. So when I put the ratios equal to each other, that means the voltages are equal to each other. From there, you get the math and finish it. Now that we know that Q4 is 46, we know the total charge on that branch, which is Q3 plus Q4. And that should be the same charge in this branch. Why? Because these two sections are connected in series. Okay. So that's why I put Q3 plus Q4, total charge there is equal to the total charge on the other side because the two branches are connected in series. I hope you got that. So from there, we got Q1 plus Q2 to be 69, and then use the same idea that Q1 by C1 is Q2 by C2. Q1 by C1 is Q2 by C2, and see what I did for Q2, I substituted 69 minus Q1. For Q2, I substituted, why? Because you can see that Q1 plus Q2 is what? 69, which means Q2 is 69 minus Q1, isn't it? That's what I substituted. And then do the math. Yep. And when you do that carefully, you're going to find that Q1 is, let's wait for it, 23 microcoulomb. Oh, that's also 23 microcoulomb, right? So we got it. Next, let's do the second part. The voltage across each capacitor, right? Voltage is charged by capacitance. So you have the charge is 23. And oh, hey, remember that both of these are in micros. So this is microcoulomb. This is microfarad. So the micros cancel out, and finally you get it in volt. Okay. So it's important to remember that. So again, V3 is Q3 by C3. Again, you have those same units there, and finally you get it in volt. Okay, 2.875 volt. That is V4. Let's move on to the third part. We have to find the voltage between the points B and A. It's going to be V1 plus V3. Why V1 plus V3? Because you have that capacitance and that here. And remember that it's going to be positive here, positive and negative. And this single capacitor is actually a combination of what, C1 and C2. That is C1 plus C2. This is C3 plus C4 because they're in parallel. And the voltage that you have across these two, we got V1. This one is V3, right? And because of the setup, you see the setup here, positive on one side, negative on the other side. That means the voltages just add up, making the difference even bigger. That's why the voltage between B and A is 5.75 volt. So here is problem number 7. Two capacitors connected in parallel produce an equivalent capacitance of 35 microfarad. But when connected in series, the equivalent capacitance is only 5.5 microfarad. What is the individual capacitance of each capacitor? So what do we have? We have two capacitances. Both of their values are unknown. But when you put them in parallel, you get a total of 35 microfarad. The same two capacitors, when put in series, you get 5.5. What are the individual values? This is you have to just use the formulas for parallel and series connection. Okay, so that's what we're going to do. C1 plus C2 is equal to 35. I'm going to keep it in microfarad because when they are in parallel, you add the capacitances. But when they are in series, you have 1 over C is 1 over C1 plus 1 over C2. But you can rearrange that to C is equal to the product divided by the sum. So C1, C2 by C1 plus C2. And then that C is given us 5.5. And I'm going to substitute for C1 plus C2 as 35. Because we know, from here we know that C1 plus C2 is 35, don't we? So that's what I've done there. So C1 plus C2 is 35. And then you get C1, C2 is the product of 35 and 5.5, which comes out to be 192.5. Okay. So now that we know the sum is 35, the product is 192.5, you just got to substitute. I have substituted for C2 as 35 minus C1, and that's going to make it a quadratic equation. Not quadratic actually, because you only have, yeah, you have to. It is a quadratic equation. So when you solve, and I have not solved the quadratic equation, you have to use minus b plus or minus square root of b squared minus 4ac by 2a. Yeah, that was like a song, and it is indeed. And when you use that, you're going to get C1 is 28.2, C2 is 6.8 microfarad. All right, the eighth one. Two capacitors, 3200 picofarad and 1800 picofarad, are connected in series to a 12-volt battery. Oh, so they are connected in series. The capacitors are later disconnected from the battery and connected directly to each other. Positive to positive, negative to negative. That means they are now connected in parallel. What will then be the charge on each capacitor? This is a good question. Well, all of the others were also good questions, but this is really good. So in the first case, you have the two capacitors connected in series to this 12-volt battery. And then both of them are going to get charged. But remember that the charges on both of them will be the same because they are in series. And then they are taken out and connected in parallel. And in this case, when they are in parallel, the voltages across them will become equal. So these are the 2 points we have to remember. And let's put it and use the math. So in the series combination, 1 over C is 1 over C1 plus 1 over C2. That means, like I showed you before, C is C1, C2 by C1 plus C2. And then put the values. I'll keep them in. So you can see that I have moved it to nanofarad. Okay? 3200 picofarad becomes 3.2 nanofarad. Okay? 3.2 nano. And that's why I have those numbers as 3.2 and 1.8. In the numerator, you get 10 to the negative 18 because you're multiplying 10 to the negative 9 with 10 to the negative 9. But in the denominator, you're adding, so you only have 10 to the negative 9. That means finally you get this 1.152 times 10 to the negative 9 farad. Okay, so we got the total capacitance. So we can now find the total charge. Because it's in series, the total charge on each one of them, Q1 plus Q2, should be equal to their total capacitance, which we just got, multiplied by the voltage. Does that make sense? So their total capacitance is 1.152 times 10 to the negative 9, and they are charged to 12. So that gives the total charge on both of them together as 13.82 times 10 to the negative 9 coulombs. Okay, so that was when you connected them in series. Now when you connect them in parallel, remember both of them were having the same amount of charge, which is 13.82 times 10 to the negative 9. But now when you connect them in parallel, charges will flow from one to the other because their voltages are not equal, but they will become equal. So on connecting them together, the common voltage is the sum of the charges divided by the sum of the capacitances. Why do we take the sum of the capacitances? Because they are in parallel. So then we get 3.2 plus 1.8 times 10 to the negative 9 in the denominator. So the 10 to the negative 9s cancel out and we get 2.764 volt. So now we know the voltage on each capacitor is 2.764. Since now we know the voltage on each capacitor and the value of each capacitance, we can find the charge on each one by multiplying the value of the capacitance with this voltage. So the charge on the first one is 8.84 nanocoulombs, and the second one is its capacitance, which is 1.8 times 10 to the negative 9, multiplied by the same voltage. So 2.764, which gives 4.98 nanocoulomb. So there are several things that you need to understand in this question. That's why I said it's a really important question. So here we have question number 9. How much energy must a 28-volt battery expend means to use, to charge a 0.45 microfarad and 0.20 microfarad capacitor fully when they are placed A in parallel, B in series? How much charge flowed from the battery in each case? Once again, a very good question. You have a 28-volt battery and you have two capacitors whose values are given. First, you're connecting them in parallel. We want to find out. So we have to find how much energy was used by the battery in each case and how much charge flowed from the battery in each case. U is the symbol for potential energy and P is for parallel. So potential energy in parallel, you know the formula for potential energy is 1/2 CV squared. In parallel, we just simply add the two capacitances. You should know that by now, right? So it's half C1 plus C2 V squared. Both are in micros, so that's why it's 10 to the negative 6. So there, I've actually added 0.45 plus 0.20. That's how I get 0.65 and times 10 to the negative 6. And the voltage is 28 volt. That gives 2.54 times 10 to the negative 4 joules because it's energy. That's the amount of energy that flows. Okay, the B part, when it's in series, again you're using the same formula, but in series, remember that the total capacitance is given by C1, C2 by C1 plus C2, right? So that's why I have that there, and then it's a matter of calculating. So that's the first one, then times the second, divided by the sum of both, which is 0.65. And then you have 28 squared, which is the voltage. Because again, you're using the same battery, which gives 5.4 times 10 to the negative 5 joules. Okay. In the C part, we know that we can also calculate the energy of a capacitor using this formula, 1/2 times the product of the charge times the voltage. So we're going to use that because this time we're looking for the charge that flowed in each case. So for A and B, we found the energy that flowed. Now we got to find the charge that flowed from the battery in each case. So we're looking for Q. That's the idea. 2U by voltage. So in parallel, we already got the energy as 2.54 times 10 to the negative 4. So we're using that by voltage gives 1.8 times 10 to the negative 5 coulombs. All right, so in parallel, that's the amount of charge that flowed. And in series, once again, we have the energy that flowed. We have the voltage. So it's 5.4 times 10 to the negative 5. But I did calculate with that number, and you get 3.9 times 10 to the negative 6 coulombs. That's how we do that. 10. I like this question. I can say that even before I read it. a 3500 picofarad air gap capacitor. So between the plates you have air as the dielectric. This is connected to a 32-volt battery. Then, if a piece of mica fills the space between the plates, how much charge will flow from the battery? The dielectric constant of mica is given as 7. So first you had air and then you filled it with mica. When you fill the space with mica, what happens to the capacitance is it goes up. It increases 7 times. And because the capacitance increases 7 times, the capacitor is able to store 7 times more charge when connected to the same battery. So it is the same battery in both cases. The voltages are equal. It's 32 volt. But on introducing the mica, since the capacitance increases 7 times, the charge that can be stored also increases 7 times. Pretty simple, right? So let's find that. So we got to find the initial charge, the final charge, and take the difference. Because the question says how much charge will flow from the battery. So here is the initial charge, which is the product of capacitance and voltage. Again, I have it in nanofarad. That's why it's 3.5. And then you get 112 times 10 to the 9 coulombs. That is the initial charge. Now, the final capacitance is going to be K times the initial. I've already told you that. It's going to be 7 times. So that will give 24.5 times 10 to the negative 9 farad. And therefore, the final charge would be that capacitance multiplied by the 32 volt. So 24.5 times 10 to the negative 9 multiplied by 32 will give us the final capacitance. That'll give us the final capacitance. So that is 784 times 10 to the negative 9 coulombs. So now we got to find the difference. See that the second number is bigger, of course. So when you take the difference between QF and QI, you get the additional amount of charge that flows from the battery. And we get it as 672 times 10 to the negative 9 coulombs is what we get. I hope you got that. Pretty simple to understand once you establish the concepts in your mind. Yeah. Okay. Number 10, a homemade capacitor is assembled by placing 2 9-inch pipe hands 5 centimeters apart. So somebody's making a capacitor at home and connecting them to the opposite terminals of a 9-volt battery. Estimate the capacitance, the charge, the electric field halfway between the plates, the work done by the battery to charge the plates, and which of the above values change if a dielectric is inserted. So there are like 5 quantities to be calculated or answered, and it's a direct substitution of the formulas. So let's do it. It's a parallel plate capacitor. So we use the formula for a parallel plate capacitor. I've shown you all of these answers together. So what I'll do is I'll just go over it. So capacitance of a parallel plate capacitor is epsilon naught A by D. So that is epsilon naught area. It's a circle. Each pipe hand is a circle, so it's pi r squared. So you have pi times the radius, and it's 4.5 inches. And I've changed it into meters. 1 inch is 0.0254 meter. So that's why you see that. So it's pi r squared divided by the distance between the plates, which is given in centimeters. So I've changed that into meter as well. And you get this as the capacitance, okay? In the B part, we got to find the charge. Charge is just the product of capacitance and voltage. Now that we know the capacitance, multiplied with the voltage, which is 9 volt, you get the charge. Electric field Electric field can be calculated in many ways depending on what's given. Here you have the voltage and the distance, so just divide the voltage by the distance. That's the voltage, that's the distance in meters, and you get it as 180 volt per meter. The work done is nothing but the energy stored. And in this case, we use half times Q times the voltage. Q is the charge, which we got here, and then you have the voltage that gives you the energy. 2.94 times 10 to the negative 10 joules. And the E says, which of the above values change if a dielectric is inserted? As soon as you insert a dielectric, of course, the capacitance is going to increase. That means it can drag in more charge and the energy. So those are the three that increase or that change. Capacitance, charge, and energy changes. The electric field, I said the electric field does not change, but got to be very careful when you say that voltage and the distance between the plates did not change. So in that context, the energy, the electric field didn't change mathematically. But remember that in a dielectric, the field produced is opposite to the applied field. So actually the electric field decreases. So keep that in mind. We come to the last question. The electric field between the plates of a paper separated capacitor is 8.24 times 10 to the 4 volt per meter. The plates are 1.95 millimeters apart, and the charge on each plate is 0.775 microcoulomb. Determine the capacitance of this capacitor in the area of each plate. So what do we have here? Here we have the electric field. We have the K value, which is the dielectric constant. Excuse me. The distance between the plates and the charge on each plate. Pretty straightforward. We know the charge is the product of capacitance and voltage. But at the same time, voltage is the product of E and D. Okay? Because we know that E, electric field, is voltage. Let me write that. Is voltage by D. So that's why we have voltage as the product of E and D. Excuse me. So that gives us C is Q by ED. All values are given. Q, it's in microcoulombs. You have E and you have D. Make sure that the millimeter is changed into meter and you get the value for the capacitance. And then when you insert the dielectric, the formula becomes K epsilon naught A by D, which if you rearrange, you will get A is equal to CD by K epsilon naught. And we know all of the values. We know that it's 4.82 times 10 to the negative 9. And then D is there. You have K and you have epsilon naught. And you get the answer as 0.283 meters squared. All right. So I hope you understood how all of these problems have been worked out. And go over it again and again until you understand them. And we'll see you on the next video.